You are 300 meters underground. The rock above you is Precambrian gneiss, 1.7 billion years old, among the most stable geological material on Earth. The temperature is 12 degrees Celsius year-round, regardless of what is happening on the surface of Labrador above you. In January, that surface is minus 35. In July, it is plus 22. Down here, it is always 12 degrees. The rock does not care about seasons. What the rock does care about is weight and pressure and the 272 cubic meters of water per second that is passing through the machine directly in front of you right now. The machine is Unit 4 of the Churchill Falls generating station. It is a Francis turbine generator combination. The turbine runner, a 5-meter diameter steel wheel, is spinning at 150 revolutions per minute. The generator above it is producing 475 megawatts. The shaft connecting them is transmitting 30 million Newton meters of torque. That torque is the conversion of the Churchill River's fall from the Labrador Plateau into electricity, and it is happening 300 meters below the surface of the Earth, inside a cavern that was blasted out of solid rock between 1967 and 1971, inside a generating station that has been running continuously with only scheduled maintenance intervals since 1971. That is more than 50 years. The rock has not moved. The machines have not stopped. The river has not rested. 5:48 a.m. The control room operator on the overnight shift checks the unit status board. All 11 units online. All outputs nominal. The reservoir level, Smallwood Reservoir, 6,527 square kilometers of stored water on the Labrador Plateau above, is holding at 471.2 meters above sea level, and within operating range, within the range it has been for most of the past 5 decades. He makes a note in the log. Nominal. Churchill Falls sits on the Churchill River in central Labrador, a river that drops 312 meters in a short distance as it crosses the edge of the Labrador Plateau and descends toward the Labrador Sea. Before 1971, this drop was a waterfall. Churchill Falls, 75 meters of free fall, one of the highest volume waterfalls in North America. A geological accident of exactly the kind that hydroelectric engineers recognize as an extraordinary opportunity. Enormous hydraulic head, available at a single point, on a river carrying the drainage of 69,000 square kilometers of subarctic watershed. The Churchill River's annual flow is large, consistent, and stored naturally by the Labrador Plateau's extensive lake system. The Churchill Falls project added Smallwood Reservoir, the result of raising the water level across an enormous area of the plateau through a series of control structures, to create a storage volume large enough to regulate generation across seasons and years. The engineering problem was not the power. The power was always there. The engineering problem was how to access it, how to build a generating station of this scale, in this location, in a climate that regularly reaches minus 40 degrees Celsius, 300 kilometers from the nearest paved road. The answer was to go underground. The decision to place the generating station underground was not primarily about the weather. It was about the rock. The Precambrian gneiss at Churchill Falls is exceptionally competent, strong, stable, when with minimal jointing or faulting in the sections where the cavern was sited. Rock of this quality can span large openings without support. The powerhouse cavern at Churchill Falls is 296 meters long, 25 meters wide, and 46 meters high. Its roof is unsupported rock. No concrete lining, no steel bolts through the entire upper arch. Just the rock holding itself. This is unusual even among underground powerhouses. It was possible because the geotechnical investigation that preceded construction identified the precise sections of rock where the span could be trusted. The excavation took 4 years. Drill and blast methods were used throughout. The standard technique for hard rock, in which holes are drilled in a pattern, loaded with explosive, fired, and the broken rock mucked out by equipment working in the cavern as it grew. The sequencing of blast rounds had to be managed carefully to control the stress redistribution in the remaining rock as the opening grew larger. A cavern is not an excavation into passive material. It is an excavation into material under stress. Stress from the weight of 300 meters of rock above, from the tectonic history of the shield, from the thermal gradients of geological time. Every blast changes the stress field. Every new opening requires the rock around it to rebalance its load paths. The engineers who designed the Churchill Falls cavern sequence understood this. They designed the excavation to work with the rock's stress, not against it. The result is an opening that has stood stable for more than 50 years, with no significant rockfall or structural intervention. The water delivery system at Churchill Falls is a feat of underground engineering in its own right. Smallwood Reservoir sits on the plateau above the powerhouse. The water must descend 312 meters from the reservoir intake to the turbine runners below. It does this through a system of tunnels and penstocks bored and blasted through the rock of the plateau escarpment. The intake structure is at the reservoir's edge, a concrete headworks with 11 intake bays, one for each generating unit, fitted with trash racks and stop logs and the hydraulic gates that control flow into the tunnel system. The intakes are submerged. The reservoir's surface may be ice-covered for 6 months of the year, but the intake structure operates continuously beneath the ice, is drawing water from a depth where the temperature remains above freezing regardless of surface conditions. From the intakes, the water travels through 11 individual penstocks, circular steel-lined tunnels, 7.3 meters in diameter, that descend steeply through the rock, following the escarpment's profile, until they reach the powerhouse cavern 300 meters below. The hydraulic head at the turbine, 312 meters, produces a water pressure at the base of the penstock of approximately 30.6 atmospheres, 30 times atmospheric pressure, on a flow of 272 cubic meters per second per unit. The steel lining that contains this flow is embedded in the rock, grouted in place, and must remain watertight and structurally sound against a pressure load that never relents while the unit is operating. The welded seams in this lining, SORM and the transition zones where the steel meets the concrete that meets the rock, are inspected on every unit outage. Because a penstock failure at 30 atmospheres of head inside a rock tunnel is not a manageable event. 6:30 a.m., Unit 7 has been scheduled for a minor inspection. The outage window is 14 hours. The shutdown sequence begins at the governor, the turbine speed controller that manages the guide vane position. As the guide vanes close, the flow through the turbine reduces. The unit's output falls. 475 megawatts, 400, 300, 200. The remaining 10 units absorb the load. The control room operator watches the grid frequency display. The frequency holds at 60 Hz. The transition is seamless. At zero output, the unit disconnects from the grid. The turbine decelerates. The shaft brakes engage. The runner, 300 tons of steel spinning at 150 revolutions per minute, takes 11 minutes to coast to a complete stop. The penstock isolation valve, 7 meters in diameter, closes against the full hydraulic head of the reservoir above. The valve actuator requires 45 seconds to close fully. For those 45 seconds, the valve is in partial position, the most hydraulically demanding condition it faces. Water flowing through a partially open valve experiences velocity acceleration and pressure fluctuation. The valve's seating faces and trunnion bearings take the loading. The valve closes. The penstock pressure drops to zero as the trapped water drains to the draft tube. The inspection team is already suited up. They enter the penstock from the powerhouse level, moving up into the now static tunnel, headlamps on, ultrasonic gauges in hand. And the tunnel is cold. The rock temperature, 12 degrees, drops further in sections where groundwater seeps through minor fractures in the lining. The floor is wet. The team moves in file, working systematically through their inspection grid. They will cover 1.1 kilometers of penstock by 11 o'clock. The powerhouse cavern at Churchill Falls has acoustics unlike anything above ground. The rock walls absorb almost no sound. The space is hard, concrete floors, rock walls, steel machinery, and the cavern geometry creates long reverb times in certain frequency ranges. The low-frequency hum of 10 operating turbine generator units, conducted through the rock and reflected from every surface, produces a background level that experienced workers stop noticing after their first week. But they notice the changes. A bearing that is developing a problem produces harmonics in the vibration spectrum that don't belong there. An experienced operator walking the generator gallery hears it before any monitoring instrument logs it. A slight change in the cavern's sonic texture, a frequency component that wasn't there yesterday. This knowledge is not formally transferable. It is accumulated through years of working in this specific space, around these specific machines, in this specific acoustic environment. The operator who notices it has been in this powerhouse for 22 years. He stops at Unit 3. He listens. He calls the maintenance coordinator. Something's different on 3, not urgent, but different. The coordinator schedules a vibration analysis for the next inspection window. The analysis, when it comes, confirms a developing issue in the lower guide bearing, caught early enough for a planned repair, not an emergency outage. This is what 22 years sounds like. The transformer gallery runs parallel to the powerhouse cavern, separated by a 20-meter rock pillar. The generators in the powerhouse produce electricity at 15 kilovolts. This must be stepped up for transmission. Churchill Falls is 1,100 kilometers from the major load centers in Montreal. At 15 kilovolts, the transmission losses over that distance would be unacceptable. The transformers step the voltage up to 735 kilovolts for the main transmission lines. 735 kilovolts. That is among the highest transmission voltages operated commercially in North America. At 735 kilovolts, the electrical field around a conductor is intense enough to ionize the air in a sphere several meters in radius. The corona discharge, the faint blue glow visible on high-voltage conductors at night, is not a fault. It is physics. It is the voltage gradient at the conductor surface ionizing air molecules. The transformers themselves are large, each one a sealed tank of mineral oil containing the wound copper coils, with oil circulation and cooling systems that must function continuously. The oil serves dual purposes, electrical insulation and thermal cooling. The transformer oil is sampled and analyzed regularly for dissolved gas content, a diagnostic technique called dissolved gas analysis that detects early-stage internal faults before they become catastrophic. Certain fault types produce specific gases, hydrogen, acetylene, and ethylene. The ratios of these gases in the oil tell a trained analyst which fault type is developing and how severe it is. The transformer oil at Churchill Falls is analyzed quarterly. The analysis has caught developing faults at a stage where planned repair was possible. It has prevented 6 forced outages over the past 30 years. 6 outages prevented is 5,700 megawatts of generation preserved per event. Power that would have been unavailable to the grid while an emergency repair was completed. The quarterly oil sample is a small action with a large consequence. The Churchill Falls power contract is one of the most studied and contested agreements in Canadian energy history. In 1969, the government of Newfoundland and Labrador signed a 65-year power purchase agreement with Hydro-Quebec. The terms fixed the price of Churchill Falls power for the duration of the contract at rates that, by the 1980s, were a fraction of the market value of the electricity being produced. Churchill Falls generates approximately 35,000 gigawatt-hours per year. Hydro-Quebec buys it at rates set in 1969. The resale value to Quebec's grid and through Quebec's transmission system to markets in the northeastern United States is many times what it costs to buy. This is not the story of this video. This video is about the machine. But the machine operates inside an economic context, and that context has shaped every decision about investment, maintenance, and future development at Churchill Falls for 50 years. The generating station has been maintained, kept operational, kept safe. I kept producing, but significant capital reinvestment has been constrained by the contractual and financial realities of who owns what and who benefits from what. The contract expires in 2041. The infrastructure will still be standing in 2041. What happens after 2041 is a different conversation. What the engineers are responsible for is ensuring the machines are still running when that conversation begins. 9:15 a.m. The surge chamber. Between the reservoir intake and the powerhouse penstocks, the water delivery system includes a surge chamber, a vertical shaft excavated in the rock above the powerhouse, open to the tunnel system below. It is 45 meters in diameter and 91 meters tall. Its purpose is hydraulic shock absorption. When a unit shuts down quickly, a fault trip, not an emergency stop. The flow of water in the penstock must be arrested rapidly. If the flow is stopped without a pressure relief mechanism, the kinetic energy of the water column in the tunnel creates a pressure wave, water hammer, that travels back up the penstock at the speed of sound in water. 1,400 meters per second, the pressure wave can reach multiples of the static head. It can rupture penstock linings, damage intake gates, stress the rock around the tunnels. The surge chamber prevents this. When the penstock flow is stopped, water rises in the surge chamber, rather than compressing into a pressure spike. The chamber volume absorbs the kinetic energy of the decelerating water column. The pressure wave is damped before it can damage anything. The surge chamber is never seen in operation. It sits in its rock shaft, full of water, doing nothing visible, waiting for the moment when something goes wrong and its volume becomes essential. Most of the best engineering at Churchill Falls is like this: invisible until needed, reliable because of the invisibility. The tail race system carries water from the turbines back to the Churchill River. After passing through the turbine runners and giving up its energy, the water exits through draft tubes, large concrete-lined channels that expand gradually to recover some of the kinetic energy remaining in the flow, and then continues through the tail race tunnel to the river outfall downstream of the original Churchill Falls site. The tail race tunnel is 10.7 meters in diameter and 780 meters long, or it operates under negative pressure, below atmospheric, because the draft tubes create a suction effect that draws the water down through the turbine and improves the effective head. This suction is limited by the vapor pressure of water. If the suction becomes too great, the water begins to cavitate, to boil locally, and the cavitation bubbles implode against the turbine runner with pressures that erode the steel surface. Cavitation management is one of the ongoing operational disciplines at Churchill Falls. The guide vane settings, the unit load levels, the tail race water elevation, all of these affect the pressure conditions at the runner and therefore the cavitation risk. Operators who have worked these units for years know the combinations that produce optimal efficiency and the combinations that begin to erode the runner's steel. The runner is inspected at every major outage. The cavitation pitting is mapped. The erosion rate is tracked. When the pitting exceeds tolerance, the runner is removed. A 300-ton lift by the powerhouse overhead crane, and repaired by specialist welders using controlled heat weld overlay procedures that rebuild the blade surface to the original profile. The repaired runner goes back in. The next inspection will map it again. This is a cycle that will continue for as long as water flows through these tunnels. The rock of the powerhouse cavern is instrumented. It had rock bolts, steel rods grouted into boreholes drilled into the cavern walls and roof, were installed during construction to provide additional confinement to the rock mass. The loads in these bolts are measured periodically using a hydraulic load cell applied to the exposed bolt end. If a bolt is losing load, if the rock mass is relaxing, if a fracture is opening, the load drops. Extensometers, instruments that measure the relative displacement between 2 points in the rock, are installed at multiple locations in the cavern walls. They have been reading since the station was commissioned. 50 years of extensometer data from Churchill Falls is one of the most comprehensive underground powerhouse monitoring data sets in the world. The data shows the initial displacement that occurred as the cavern was excavated, expected, modeled, EO accounted for. It shows the subsequent stabilization, the rock mass reaching a new equilibrium after the excavation of stress redistribution. It shows in some instruments no detectable movement in the past 30 years. The cavern is stable. It has been stable. The data says so. But the instruments keep reading, because structural confidence is not a conclusion you reach once. It is a status you verify continuously. 1320. Unit 7's inspection is complete. The team found minor surface oxidation on 2 penstock liner plates, within the acceptable range for the current inspection cycle, photographed and measured and entered into the maintenance database. The valve seat inspection was clean. The draft tube interior showed cavitation pitting consistent with the last inspection. No acceleration in the erosion rate. On it right, the unit is cleared for return to service. The penstock isolation valve begins to open. This is the most hydraulically dynamic moment in the unit startup sequence. The moment when 30 atmospheres of head begins moving water through the penstock toward the still-closed turbine guide vanes. The water fills the penstock volume, and the pressure builds at the guide vane inlet. The operator at the control room watches the inlet pressure gauge climb to its operating value. The guide vanes begin to open. The runner begins to turn. In 4 minutes, Unit 7 is at 475 megawatts. The control room operator updates the unit's status board. 11 units, all online, all nominal. The Cavern hum, which has been one voice short since 6:30 this morning, returns to its full chord. The Churchill River below the powerhouse outfall is regulated. What once thundered over a 75-meter waterfall now emerges from a concrete outfall structure as a managed flow. The combined output of 11 turbines, measured and controlled by the guide vane positions, set by the control room operators. The river still flows. The flow is different, more consistent, less seasonal. The extreme spring peaks that once occurred when the plateau snowmelt ran unconstrained into the river have been absorbed by Smallwood Reservoir, stored and released on the electricity market schedule rather than the watersheds. The town of Churchill Falls exists because the generating station exists. It was built as a construction camp and converted to a permanent community. Its population is roughly 700 people. Every function in that town, the electrical supply, the heating, the water treatment, depends on the station operating. The station sustains the town that sustains the station. This is circular infrastructure dependency at a small scale. It makes the reliability of the generating station not just a commercial obligation, but a community life safety function. The operators who work here know this. It does not make them anxious. It makes them careful. Churchill Falls produces 5,428 megawatts of installed capacity. In annual energy terms, accounting for scheduled outages and flow variability, the station produces approximately 35,000 gigawatt hours per year. To put that in perspective, the entire electricity consumption of the province of Newfoundland and Labrador is approximately 6,000 gigawatt hours per year. Churchill Falls produces nearly 6 times what the province uses. Almost all of it goes to Quebec. The transmission lines, 4 735 kilovolt AC lines running south from Churchill Falls through the Labrador wilderness, carry the power to the Hydro-Quebec system, which distributes it across Quebec and exports the surplus to the northeastern United States and Ontario. The physical path of that power from a 300-meter underground cavern in Labrador to a home in Boston or a factory in Montreal spans 1,500 kilometers of some of the least inhabited land in North America. It happens continuously. It has been happening since 1971. The rock holds, the machines turn, the water falls, and 300 meters below the Labrador Plateau, in a cavern the size of a city block, the overnight operator checks his status board one more time before the morning shift arrives. 11 units, all online. The readings are nominal. They are almost always nominal. That is what 50 years of engineering discipline produces. Under this video, there's a subscribe button. It's a small action, but it helps keep stories like this afloat. If these systems fascinate you, the quiet force of water held in place by engineering and discipline, subscribing simply means you want to see more of what operates beneath the surface.